Hey, what's up guys? Hope you're all doing well. I'm Arvind from PrecisionDataScience. Today we're going to be working on Kaggle's Bank Churn prediction dataset. In this dataset, we have customer information and we're going to be building a machine learning model to predict whether the customer leaves or not. So without further ado, let's dive into the video. First, we'll import NumPy and Pandas to work on the array data and data frame. Next, we have Matplotlib and Seaborn for data visualization, and then ignore the warnings to have a cleaner output. We'll read the two CSV file, train and test file, using read_CSV method and assign it to a data frame df and df_test. We'll display the first few rows for each dataset using head method. And here we can see the columns data such as ID, customer ID, surname, credit score, geography, age, balance, estimated salary, etc. for both train and test data. One thing that distinguishes the train data and the test data is the presence of exited column in the train data, which shows the status whether the customer exited or not. For the test data, we need to create the exited column, make predictions, and submit to the Kaggle computation for results. dfinfo method provides a summary of data frame, which includes missing data and data types for each column. Here we have around 165,000 entries and all are nominal values, which means that there is no missing data. With df.nUnique method, we can see the number of unique values in each column, and generally columns with categorical values will have less unique values. Since customer ID, and surname are unique to each customer and may not play a role in deciding whether customer will churn or not, we can drop these columns with the drop method. So before that, we're going to assign the ID values from the test data to a new variable test_ID so that it can be used to make predictions on the test IDs. We'll plot the histogram plot for each columns and see the distribution of data for both train and test set. Here we can see a similar pattern in both train and test data. Some columns have numerical data similar to a normal distribution, and while few other columns have categorical data in imbalanced form. We can check this imbalance by applying value counts method to, let's say, exited column, and we can see that we have less data for the customers who churned. Next, we'll assign the columns with the object data type to variable categorical columns and display the categorical columns. As you can see here, we have two columns with object data type, that is geography with few countries and gender with two categories. In order for the machine learning model to work, we need to convert the categorical data into numerical values. For that, we'll use one-hot encoding technique to assign each category to a separate column. Pandas has a simple method called getDummies, which applies the one-hot encoding technique to the categorical columns. We're going to apply the method and check the columns after one-hot encoding. With df.columns method, we can see that the geography column has been replaced by 3 columns representing the presence of each country, and gender column has been replaced by 2 columns representing the presence of each gender. Since one column is enough to represent 2 genders and 2 columns are enough to represent 3 countries, we're going to drop the geography Spain column and gender male column. We're going to see the top 5 rows with the head method, and we can see that the object data type have been replaced by boolean values, that is true or false. Next, we'll convert the data type to float and plot the correlation heat map with values sorted in the decreasing manner. The correlation value have been annotated, and here we can see negatively correlated features such as number of products, whether the customer is active member or not, etc. And we have positively correlated features like age, balance, estimated salary, etc. Next, we need to handle the outliers. For that, we'll select the columns that needs to be clipped and compute the Q1 and Q3, which is nothing but the first and third quantiles. We'll compute the IQR, that is the interquartile range, which is the difference between Q3 and Q1. We're going to compute the upper and lower limit, which is given by these formulas, and anything outside of these upper and lower limit are considered to be outliers and need to be clipped within this range. This range can be easily explained visually using box plot, and we'll try to compare the data before and after clipping for both train data and test data. The figure on the left shows the box plot before clipping, and the figure on the right shows the box plot after clipping. We can run the process for both training and test data using for loop and see the vanishing of the outliers visually. For some columns, we can see that there are no outliers and hence there is no change, while for others, the outliers have been clipped. In order to make predictions, we have to separate the features and the target column of the trained dataset. For features, we are considering all the columns except the target column, that is exited column, and for target column, we are considering only the exited column. For training the machine learning model, we need to split the data into training and validation set. For that, we'll import train test split from the scikit-learn library, and we'll consider 20% for the validation set and 80% for the training set with a random state to maintain consistency. Next, we'll balance the data using smooth technique and apply it to the training data. Moving on to machine learning model implementation, here we are using XGBoost Classifier, which uses gradient boosting method, that is combining weak learners with a learning rate and a regularization in enabling them to evolve into a strong machine learning model. We'll instantiate the model with the same random state and fit the model for the training data. After the model learns by fitting the data, we're going to predict the label values for the validation set. For evaluation, we're going to port certain metrics such as accuracy, F1 score, classification report. So here we have accuracy of around 86% and F1 score of around 78%. Next, we'll plot the ROC curve. ROC curve plots the true positive rates against a false positive rate. So generally, the true positive rate is the name for recall, and the false positive rate is the ratio of negative instances that are incorrectly classified as positive. We'll find the probability values for the validation set and assign it to a new variable y_prob. We're going to compare the values with validation set and find the true positive rate and the false positive rate. We'll plot the ROC curve, and here we have ROC score of 0.8896. To verify the values, we're going to do a cross-validation score across the dataset using cross-val score from the scikit-learn library. We'll apply the cross-validation across the training set with a scoring as ROC_AC and cross-validation of 5 folds. After displaying the results, we can see that the mean value is 0.9688, which is higher compared to the validation predicted score. The system ends up performing well on the training set and may not likely perform well on the test set. So now, in order to make improvements to the machine learning model, we'll try to optimize the parameters within the XGBoost. For that, we'll be using RandomizedSearchCV for optimization. We will import the RandomizedSearchCV from the scikit-learn library and create a search space for all the parameters to be searched. Here, we're considering an estimators, max step, learning rate, gamma, lambda, etc. as parameters. We'll instantiate the RandomizedSearchCV with estimator as XGBoost model, parameter grid for searching as search space, number of iteration is set to 50, scoring as ROC, and cross-validation as 5 folds. We'll fit the randomized search CV for the training data and let it search for the best parameters. In the end, we'll print the best score and the best parameters. Okay, after printing the best score, we have an improved ROC score of around 0.9699. We will quickly check the important features for best score as they indicate the relative importance of each attribute for making accurate predictions. Here we have number of products, is active member, etc. as the important features. We'll print the best parameters and run the machine learning model with the best parameters to check the improved ROC score on the validation set. After displaying the score, we can see the accuracy and F1 score have minor changes, while ROC score has some improvements, which is higher compared to the previous predicted score. Next, we need to save the model and create predictions for the test set. For that, we'll import the joblib library and save the machine learning model for the optimized parameters so that we can use it whenever we want in the future without training the model. After saving the model using the dump method, we'll load the file for making predictions. We will predict the probabilities for the test data and create a data frame using test_id as the index. We'll save the CSV file and make submission in the Kaggle website. After submission, we got a score of 0.88492, which is within the top 50%. If you want further improvement, you can refine the parameters in the search space and let me know your best score in the comments. So that's all I have today, guys. If you enjoyed this video so far, please like the video, share, subscribe, and hit the bell icon to see more content. Thank you.